Hello everyone, welcome back to class. It's just 2 minutes or so until it's 2:30, but for now, welcome and I'm glad you guys are here. We'll get our meeting going and then we'll be good to go for today. Hi there, Jillian, Melissa, Flavio, everybody else. Great to see you guys. Hope you had a nice weekend. All of a sudden, out of nowhere, it's like kind of fall weather, right? All of a sudden, it's kind of cold, so that was a change of pace. Hi, guys. Hi, Lena, Nicholas, Hannah, everybody. Just another minute, pretty much, and then we'll really get into it. You like the cold better than the heat? You know, it kind of, there's all kinds of preferences about that. I usually like the heat, but I don't like it to be hot 10 months out of the year. So, you know, I get a little tired of it, I guess, by the time we get to November. So it's a good time to have some cooler weather. But I usually, I run a lot and stuff. And so for me, running in the cold is a little harder than the heat because it keeps you loose at least. No, there's no meeting Wednesday. No, good question. But no, it's Veterans Day on Wednesday. So not just me, but I hope all your other professors are also not holding class because I think, you know, it's a school holiday. Is that the case though, Elena? Do you have other professors that are saying, no, we're still going to meet? I would hope not. Don't they want a day off? Okay, well, thanks everybody. It's 2:30. Thanks for being back. Let me just talk to you guys about what the plan for our meeting is today. And it's all just as listed in the schedule on the syllabus, so none of these dates or anything are different, but just as a reminder, Monday after we come back from the long break, because, you know, Wednesday is Veterans Day, I was just mentioning this, so 2 days from now, Wednesday, we don't have class. There's no lecture on Wednesday. Your third homework assignment is still due on Wednesday before class time. So you have to just send me a file with your homework number 3 anytime before 2:30 p.m. on Wednesday. But we won't be meeting and there won't be a lecture provided for on Wednesday. So hopefully that's clear to everybody. It's a school holiday for Veterans Day. It's kind of, I think, I'm not sure if I remember in the past that they gave us the Wednesday off. I think usually they just selected it as a Monday or something. But anyway, this time it's Wednesday, the 11th of November that we get off. So 11/11, no class. We will be back though in a week on the, 16th. And on the 16th is when you have your third quiz. The third quiz is all about chapter 12. It's all about this science topic that we're going through. So today's lecture is important on that basis because it's the second part of the chapter 12 lecture. So the notes and material discussed last Wednesday and today is the type of information that's going to be used on the upcoming quiz. So as we look forward in the schedule a little bit, Wednesday is due date for homework 3. Monday, coming back from the long weekend, is the third quiz. And then as we continue, we'll just get into new chapters, and at the end of the class, there'll just be one more homework assignment and then the final exam. Okay, so any questions about all of those things at all? If there are, please let me know. As usual, if you have questions about this or anything else, I'm always happy to clarify or explain. But if that sounds clear enough, then we will go right back to our chapter 12 notes. There's still a little bit more to say on chapter 12, and so we'll see if it takes us the whole meeting to cover it. And wherever we end, that's where we'll finish with our notes on chapter 12. Okay, so chapter 12, current chapter, all about science. So let me just get my notes open. All right, so when we were here on Wednesday last week, yes, the next quiz will be Monday. And that's just as you see listed in the syllabus. Monday, November 16th, is quiz number 3, just on chapter 12. It's not on anything else. It's just on chapter 12 by itself. So just stay up on the syllabus if you can, and I try to provide updates as we go through the course, but we've been on schedule so far, which is good. Okay, so in chapter 12, it's all about science. I'm just reviewing some of the topics from last time, and then we'll move forward in the notes. The topic of chapter 12 started just by defining science. So what is science? Science is reasoning from observable facts. So you just start by identifying facts, collecting data about the world, what's happening in it. But then you want to be able to explain the existence or the occurrence of these facts. So like, water's coming out of the sky. That's a fact. Why, though, is it happening? A scientist then tries to give you some kind of explanation as to the cause of this observed fact. So scientists observe the world, see what the facts are, try to explain the reason these things happen, and give you explanations that could be tested to verify that they're the correct explanation. So again, it's testable explanations for observable facts. Let me make it clear again. No, there's no class on Wednesday. And let me ask you a question. Are your other professors holding classes on Wednesday? Because that's what I want to know. Is there anybody in this class, in this meeting, who has some classes to attend on Wednesday? Let me know, yes or no? No? Okay, good. There shouldn't be, because it's a day off. So no, there's no class on Wednesday. It's Veterans Day. Veterans Day, when we honor the veterans of the United States military who've died and served in the past and current day still living. So Veterans Day. For the study guide, well, I've given you guys some study guides. I think at least we've talked in general about all the topics upcoming on exams and stuff. So yeah, I'll definitely give you guys a sense of the things to expect. But all the topics, all the definitions and terms that are discussed in chapter 12, they're all fair game for the upcoming quiz. And I'm reviewing some of those things right now. So if you're just following my discussion and taking your good notes and reading the chapter, obviously, then you'll have no problem. Okay, so first of all, definition of science is what the chapter begins with. After that, there's some discussion of some important figures in the scientific revolution and in the early history of Western science. So they talked about Nicholas Copernicus, who basically launched the scientific revolution with his discovery of heliocentrism. The heliocentric model of the local solar system replaced the older geocentric view of the cosmos. Heliocentrism means that the sun is at the center and we rotate around it. Geocentrism, the older idea, was that the earth was at the center and everything revolved around the earth. It was considered very important back then to hold on to the idea that the earth was at the center because it was considered something that was a religious, orthodox view. The church at the time assumed that God would never have made the earth in a random place that's not at the middle of everything. So when Galileo and Copernicus used telescopes to determine that we're not at the center, that was considered quite controversial and even resulted in threats being given to at least Galileo to recant his testimony. So Copernicus is mentioned as one of the founding fathers of Western science for his discovery of heliocentrism. He was a Polish astronomer who lived from 1473 to 1543. We then discussed briefly Sir Francis Bacon, and his historical legacy is that he was a British philosopher and scientist who basically did the steps in the scientific method that we still use to this day. So another major figure in Western science. After that, we all discussed some of the main assumptions that are built into science. So these are not notes that I'm writing only because we covered it on Wednesday last week, but you can refer back to the more detailed notes then. I'm just sort of summarizing. But what are some of the assumptions behind science? One of them is empiricism, which we should know by now is the idea that most human knowledge comes from the 5 senses and observation. Hi, Alex, good to see you. Another main assumption in science is the idea of objectivity. That is the belief that we can learn about the universe, the world, as it really is, and that we can get to those true objective conclusions without bias. So the belief in objectivity is the idea that we're not just out here talking about our personal subjective feelings or opinions, but that there are real hard facts, and that we can find out what those facts are and that we can get there without bias, etc. So another assumption of science is objectivity. Then there's the assumption known as materialism, or some call it physicalism. Does anybody remember what that one is, really quick, just to throw that out there at you? What is a viewpoint called materialism? This is a belief about something. What is the belief of materialism? Who knows that one? Let's see if you could tell me. Don't hold back. Just let me know. What is materialism? Just full force. Let me know. Okay, Natalie, everything in the universe is made up of physical matter. Good. Including even what? Everything, yes. And even this one little extra thing that sometimes people don't think is made out of just matter, including us. Good, and that's key to include. It's also inclusive of us and our consciousness. You know, the very fact that you're able to even see and hear and witness this lecture, that you can think about, I don't know, what you were doing over the weekend and have memories. Having a mind with thoughts and so forth is also, according to materialism, just based on the existence of the physical brain and the neurochemistry of the brain. So, okay, good. Science also assumes materialism, that everything's made out of matter, and not just everything except for the mind, but the mind is also just made out of matter. It's made out of, you know, cells, which if you break them down far enough, you're going to get to the level of atoms, electrons and protons and stuff, but everything's just made out of matter. Okay, so that would be materialism, which would deny the existence of anything supernatural like a soul or a spirit or ghosts or anything like of that kind. Okay, another assumption in science is predictability. That's the assumption that the whole universe is orderly and predictable. So cause and effect relationships that we've discovered or figured out, they're never going to change. They'll always remain the same throughout all of time and space. So the property of like gravity, you know, which acts on massive objects that attract each other. Well, will gravity kick in if I allow this marker to escape from my grasp? Let's see. I think it will. That's my prediction. And it did happen. How did I know it would happen? Well, because this seems to be the way that the law of gravity operates. And that's how it has always worked before. But what is my guarantee that it will continue to function in the same way on and on into the future? Well, that is just an assumption that science makes, that these laws of nature are stable, that they're permanent, and that there are no exceptions to them. So it's like gravity isn't just going to work today or tomorrow, but for all time if we reproduce the same physical conditions. Okay, and then one more assumption of science was unity. That was the belief or idea that the whole universe is unified, and therefore that means that there could be one set of scientific laws that could ultimately explain everything. The grand unified theory. This is a hoped for end result of scientific research. So we will have a comprehensive physical theory of everything that can explain the behavior of the biggest and the smallest scales of reality. Okay, and then the last thing, that's just my review of last meeting, were some limitations of science. One of them was that science, of course, assumes that there is an external world, that the world is not just a dream you're having or some kind of figment of your imagination. We have to assume there's an external reality aside from just your thoughts. Otherwise, what would be the point of investigating reality if it was all a big dream? So science assumes the existence of the external world, which technically can't be proven, but has to be given as an assumption. There's also the assumption in science, or another limitation in science, I should say, sorry, that it can only study the things which are either directly or indirectly observable. Yeah, maybe we are in a simulation. The simulation's been very interesting this year by whoever's programming it. But yeah, I mean, there'd be no way to prove whether that's true or not. But science just has to assume not. Okay, now also, science can only consider and study things that are observable. So if there are things that escape the possibility of detection or even indirect observation, then that would be very hard for science to grapple with or to understand. And some people also think that the predictability assumption is fair criticism for that, because how can you really know that natural laws, which have heretofore always operated in one way, will never ever vary or change in the whole future? That's something that is assumed, but I guess can't be proven. Okay, so then after that, the next little point that's discussed in chapter 12 is what are some attitudes that people have basically between the relationship of science and religion? You know, because much has been said about how the two realms don't always agree, and in some cases you can even argue are really in conflict with each other, that they don't say the same things, that they even state incompatible and opposite things. But what is the deal? What are opinions or viewpoints that people can have in terms of the relationship between science and religion? So the textbook refers us to four. There are four possible attitudes, four views about the relationship of science and religion. Okay, so 4 views about this relationship, and I'll put them here and discuss each one. So first of all, some people would say that science, when it comes into conflict with religion, like if they don't agree, if they say something opposite to each other, some people will say, well, if you got to take a choice and you got to pick a side, if they don't agree, then that one person might favor science over religion. That's one option. So some people will say that science takes priority over religion when the two conflict. Okay, so that's one possible attitude or viewpoint. And let's think about like an area where science and religion might not agree. And I'm generalizing a little bit because I know that not every single person who believes in religion agrees with some of these claims, and not everybody who follows science as their primary source of knowledge agrees with the other. But in general, okay, let's suppose that there are definitely some religious people who would argue that evolution is false, that mankind was created fully in the image of God, and there wasn't like a very gradual process of adjustment to the environment that led from apes specializing and adapting and eventually becoming these bipedal hominids that we are, the Homo sapiens. So there's a conflict. What's the real truth? Is it creationism or is it evolution? Well, those are opposites. They're not in agreement with each other. They disagree with each other. So if you hold this viewpoint, and this is your attitude, then you would say I break in favor of science when these disagreements occur. So if science and religion don't agree, like I don't know about the age of the universe, could be another one. In some religious denominations, it is believed that the whole planet Earth is merely like 6,000 years old. And of course, fossil data, carbon records, carbon dating of fossilized material, and spectroscopy of the electromagnetic spectrum that we can observe from the Earth's surface. It would indicate that the planet Earth is billions of years old, and the universe is even billions of years older than that. So that's a disagreement, right? Science telling you that we're in a universe that's billions of years old, and some religions saying, no, it's only been here for a few thousand years. Which one to agree with? Well, if you hold to this viewpoint, then you prioritize science over religion when there's a conflict. So if it was creationism versus evolution, this type of individual would say, I'm going with evolution and I'm rejecting the claims of the religious side. Okay, but that's only one attitude. Okay, there are others, and the next one is just like the flip side of that. So the reverse would be the position that religion takes priority over science when the two come into conflict. Okay, so some people will go in the opposite direction and say, if there's a disagreement between the two fields, I'm going to favor the religious explanation and reject the scientific account. Okay, so this would be like a person who's heard the theory of evolution and also understands the claim of creationism and says, well, they don't agree, but they cannot both be correct, so I'm in favor of the religious answer to this question. All right, so not everybody's the same. People have different attitudes and views. I'm just trying to show you what these views could be that people could have. And you've probably met either type of person. Some people just say, oh, religion is supernatural, or maybe based on superstition, or maybe it's unscientific, and they're going to maybe hew more closely to this worldview. Other people will say, I don't know, science doesn't know everything. Maybe the scientific community presumes that it has knowledge that's really not there. And maybe there's some kind of misinformation or false assumptions that have been found there. So some people are going to just tend towards the religious explanations of the world. There's two more possible attitudes. So I'm going to need a little space, so I'm going to erase these and then write where that space is. The third one would be that they are actually dealing with different topics. So science and religion deal with different topics, and that would mean that they don't conflict. That's another attitude that you've heard some people give. It's the idea that religion and science are in separate lanes. They're not really talking about the same stuff, and therefore they don't have the potential to overstep their boundaries and contradict each other. So one person might think science is where we look to when we're trying to get a physical explanation of a cause and effect relationship. So if you want to know how like photosynthesis works, or how planetary orbits work, or how gravity functions, then you'd look at science. But on the other hand, someone could argue that religion is not at all interested in that stuff. Instead, religion is concerned with spiritual questions and morality, and whether you're living in a good moral example. So you can argue that science and religion have their own separate spheres. Like a Venn diagram where two spheres can have an overlapping center area. Well, this would be the idea that there is no overlap, that each one is on its own separate topic. You've got religion to deal with the moral and spiritual questions that we find interesting, and you've got science to deal with all the cause-effect, physical explanation stuff. So that's another view, and this is the kind of view someone holds if they don't want there to be like these strong conflicts in between science and religion. They would say, well, those conflicts only appear to exist when you think they're both talking about the same material, but they're not. At the same time, as much as I've seen a lot of people hold on to this perspective because they basically just want to have it both ways, it's a little hard to sustain, because obviously there are claims that you can find in religion that appear to talk about some of the same stuff that science is also interested in. Like science and religion both deal with cosmology, meaning the origins of the universe. So in science, we talk about the Big Bang and the early conditions of the physical universe in the expansionary, inflationary period after the Big Bang. In religion, it's all about the act of creation by God, and in Genesis, how there were 7 days, and on the seventh day he rested. So in a way, it's also hard to disentangle the two and say they're not at all involved in the same subject matter, because science and religion both talk about the origins of man, about the origins of the universe. So there do at least superficially appear to be some disagreements. But anyway, there's a third view. And then the fourth one is this. The fourth attitude or view could be that science and religion are compatible. So they're actually not disagreeing, because if you just interpret them the right way, then they're not saying different things, they're saying the same thing. So that's the fourth view. Science and religion are compatible. Okay, so, and then hi Kayla, good to see you. I saw you there just as you joined the meeting. So this fourth perspective or viewpoint about the relationship of science and religion, that the two things are compatible. According to this idea, it only looks like religion and science don't agree about certain things, but in the end, they really do agree. It's just that sometimes you might have to be a little bit more creative in the way you interpret the religious information. Okay, so like maybe you've heard people make this kind of case. So someone is told, okay, so like in the Bible it says God created everything in 7 days. On the seventh day he rested. So what that would mean is that within 7 days of creation, human beings and animals and the planet Earth, it was all there. But according to science, that's not true at all. According to science, it took billions and billions of years just for matter to accumulate in such a way that it could form the stars and the planets. And it took billions more years after that for human beings to emerge from primordial life forms into the highly specialized and intelligent mammalian vertebrate forms of life that we are today. So that looks like a big difference. Religion saying it only took 7 days for God to make everything, and science saying it took billions of years for the universe to sort of just take on the features that we see it having today, including life. Now, that could look like a disagreement. The Bible says 7 days, science says billions of years. But somebody could argue that, well, it only looks like they disagree, because if we just reinterpret the religious doctrine, then we can make it consistent with the scientific explanation. Do you know what I'm saying? Like somebody could argue that when it says in the Bible that God created everything in 7 days, a person could try to finesse that so that it's on the same page with science by saying that really means what under interpretation. Can you guys or anybody think about what this subtle alternative interpretation of the literal statement could be? so that it's no longer something that is in tension or contradictory towards science? Can I restate the question? As you're thinking about it, please write your answer in the chat when you've got your mind wrapped around this. But the only question I'm asking you is there any way that a person could take a different interpretation of the religious scripture so that it really means the same thing as what the scientist is arguing when we're talking about how long it took for mankind to emerge? What's the answer? 7 days or billions of years? How could a person argue that there's no contradiction here? Think about that. Please tell me. I need you to give me something feedback-wise in the chat. So what could be this, you understand, interpretation of the religious doctrine that would make this all make sense? So Natalie, you're writing down 7 billion years. Maybe can you expand on that, or anybody else? Oh, I see what you maybe mean. 7 days stands for 7 billion years or something like that. Is that kind of what you were trying to indicate there, Natalie, I think? Yeah, so you could argue that, well, you know, the scriptures, they say 7 days, but it doesn't necessarily like literally mean 24-hour days, like how long it takes the planet Earth to rotate on its axis so that, you know, we see the sunlight and then the dark and the cycle repeats. You could argue that in the Bible where it says 7 days, that's an arbitrary unit of time. These are days in the mind of God. And so what could be such a day, 1 billion years, 2 billion years? Now it becomes something kind of, in a way, more flexible, so that we can say, oh, science and religion, they look like they don't agree, because science says we've only been here for 100,000 years and the universe is billions of years old. In Genesis, it says everything was created in 7 days, but maybe Genesis really didn't mean something different. Let me give you another account, okay, another example, rather. Science says that we have evolved. Religion says, no, we were totally created in this image right from the beginning. Now that looks like a totally different viewpoint, but someone could argue, oh, well, when God created man, he just created the conditions that would lead to the existence of man over a long span of time. So you can argue that evolution is actually part of creationism, and that's why there's really no disagreement. The two things, you just have to work a little harder to see your way through to how they're really saying the same thing. It's just the language used and the manner of describing it is a little different. So that's a fourth option. But, you know, it's tough because if it really was true that we should interpret these biblical doctrines in a way that is less literal, then why wasn't it written in that less literal way? You know, I mean, a day, everyone understands how long a day is. It's 24 hours. So if this was just some arbitrary unit of time, then how come they didn't say something different? Some people argue that this is, in a way, ad hoc reasoning. Like, so after the fact, after the scientist establishes their claims, we go back to the original text of the Bible. And now we're trying to reinterpret it in a way to align with whatever the scientists are discovering. You know, but nobody would have thought of this reinterpretation if the scientists just didn't do their own independent fact-finding. So some people think that this is a way of trying to reconcile the two areas, but that it's somewhat intellectually dishonest, or that it's, you know, trying to create consensus where there actually isn't any. But anyway, that's a couple of points about views concerning the relationship of science and religion. So to the person who prioritizes science over religion when they conflict, that's more of like a secular person, maybe an atheist or a scientific realist. To the person who favors religion over science, that's going to be a more devout, traditional practitioner of religion. And in these other two cases, that's people who want to see that the conflicts either don't exist or they're being misinterpreted. Okay. So now that we got that, we move on to the next part of our notes on chapter 12. And the next thing that's discussed is the scientific method, all right? First thing I want to do before we go into the scientific method, well, actually, I'll do that later. So first, I just want to explain all the steps, okay? And in the textbook, they refer to 5 different steps of the scientific method. So steps of the scientific method. Okay, so the first initial step is to identify a problem. Okay, so the whole method, the whole procedure starts by identifying some unexplained phenomenon in the world that we want to know how it works. We want to get to an explanation of how it happened that we don't have yet. But that's where we start. So if there's no problem to explain, then there's nothing for the scientific method to operate on. So there has to be some observed phenomenon in the world that is not totally understood yet. So observe the world and identify an unexplained phenomena. So something that happened, but that we don't exactly know why it happened yet or how it happened. The goal of this method will be at the end to give us an adequate explanation for the phenomenon identified in step one. Okay, but you got to start somewhere. So this problem could be any number of things. For example, there's this event that's occurring globally now called bee colony collapse disorder. And what it shows is that the population of bees worldwide are going significantly into decline. And that's something that not everybody really understands why. Why is that happening? So that's a phenomenon. That's a problem. And we're just trying to figure out what's the cause for it. You know, you could look at the planet heating up and sea level rising, and you could say, oh, okay, that's something that's happening. Let's try and explain why it is happening, all right? But you got to start with the problem to be explained, a phenomenon that you're trying to give an explanation for. Okay, so, but that's not where it ends. That's just the beginning. The next step of the process is to develop an initial hypothesis. Okay, so now at the second step, you try to give an educated scientific guess that can explain the occurrence of the observed phenomena. Okay, so okay, so a hypothesis is just kind of a fancy science word for an educated guess. A hypothesis is an educated scientific guess to explain the occurrence of an observed phenomena or event. So we call it an initial hypothesis because it's subject to revision. It can be altered a little bit in the light of your initial fact finding, or of course, if you conduct an experiment which tends to disprove the hypothesis, then you're going to have to come up with a second one. But you know, you do your best to come up with some initial formulation of why could this thing have happened. So like, I don't know, bee colony collapse disorder. If that's the problem being identified, there could be different theories. Well, let's call them hypotheses at first. So there could be different hypotheses to explain that. Maybe one is this. It seems like the decline in the number of bees is somewhat correlated with the onset of wider cell phone telecommunications. So could it be that the development of all these 4G and 5G cell phone towers is producing a kind of radiation in the Earth's atmosphere that is harmful to the life cycle of the bees? Maybe that's one theory. Maybe another theory is that it has to do with changing weather patterns that have forced them into migratory patterns that are harmful to their well-being or survival. You know, maybe there's another type of explanation. Could it be that there's an overgrowth of a certain type of predatory insect that uses bees as their primary source of food, and for some other unrelated or just indirectly related reason they have become more populous? So, you know, an initial hypothesis will simply take some perspective on why the event occurs. But then we go on from there, right? So we start off with just some problem to be explained. I'm going with like a random example used in the book of the bee colony collapse disorder. But anything under the sun that could be of interest to a scientist or a human being could be another identified phenomenon. We move on from that to try and state some educated initial guess as to why this thing has happened. So at the third level of a scientific method, we want to refine the hypothesis. And so that's what the third step is. Gather additional data and refine the hypothesis. Okay, so this is just about making any adjustments that might be necessary to your hypothesis, tweaking it, altering it in light of your initial fact finding. Okay, so sometimes your initial hypothesis has to be just narrowed down a little bit or made more specific in some area, and that's what this step is all about. So adjust the hypothesis as needed based on your initial fact finding or data collection. So okay, so for example, there seem to be like very high rates of depression and even suicide with young people in the current day. And you could say, oh, well, that's a problem that we observe, right? That's just a phenomenon. Like suicide rates are increasing with younger and younger people. Now, there could be an initial hypothesis that somebody gives about that. Like, could it have to do with social media? Because social media, of course, has exploded since, you know, the mid-2000s, 2005, I guess, was sort of the start of Facebook. And, of course, nowadays, a lot of people are doing a lot of more stuff on not just Facebook, but all kinds of other social sites. So you could argue that, well, this graph that shows an increase in, you know, teen suicide and everything, it's also correlated with the same time period where social media engagement goes way up. So here's an initial hypothesis someone might have. I believe that the increased rates of suicide and depression in young people has to do with the rise of social media. But suppose that as you start to, you know, investigate this hypothesis, you notice certain patterns, like, oh, it's not just all social media sites, but maybe just some, like maybe the photo sharing sites. So now you're narrowing your hypothesis down. It started off as young people are more depressed nowadays because of social media engagement. But now you're saying, oh, it's social media of a specific kind, like photo sharing sites. And then maybe you even get it narrowed down further, like, oh, and people who are on these photo sharing sites for more than like 3 hours a day. So now you're narrowing the hypothesis down a little bit, making it a little more specific and tailor-made to the facts that you're learning about as you start to collect data. And that's how sometimes this refinement of a hypothesis might work. I don't know, there's been a lot of school shootings in the past 20 years, really. And until the pandemic started, it was getting to be a real problem, you know, happening almost every other week, every couple of weeks. So, and not just schools, right, but just mass shootings in different public places, churches, and all kinds of horrifying scenarios that have really happened. Now, that's something that didn't happen so much back in the 90s, 80s, 70s, and before. So you could say, oh, well, here's something that we see, increasing incidence of mass shootings in public in America. What could be an initial hypothesis? Maybe somebody thinks, I don't know, could it be violent video games? And then maybe they start to collect data on that, and they notice that it's not just violent video games described in a general way, but maybe like first-person shooter genre games, and maybe only people from like some socioeconomic background who have access to those games and play them a lot. So now, you know, the hypothesis, which started off a little more generic and broad, has been narrowed down and made more precise. So anyways, once you've gotten your now refined, tight hypothesis, we move to the all-important fourth step. This is maybe, you know, the most important step, and it's to test the hypothesis. Okay, so that's step 4. All right, so when you test the hypothesis, basically, either in a real world or a laboratory setting, you conduct an experiment that can either confirm or disconfirm the hypothesis. So that's the idea here. Either in a real world or laboratory setting where you can control things. One conducts an experiment which will either confirm or disconfirm the hypothesis. So you really have not completed the scientific method until you've done a test, until you've tested the hypothesis. So you can't just be like, yeah, I think these bees are dying off because of the cell phones that are emitting radiation. Done. There's the theory. That's the explanation. No, you have to test it, right? Science is all about testing. It's not just people like spouting off their views and saying, that's just what I think. I can't prove it, neither can you. That's just an opinion. No, science needs to have the ability to make experimental proof. So let's see. If you were the scientist who had this hypothesis about the bees declining in number because of exposure to, let's say, cell phone radiation, how do you think that could be tested? Like, what materials do you think would have to be established for us to maybe test this? Maybe we have to have two groups of bees, and let's see if you can tell me what might follow from there. The hypothesis that is to be tested is bees die off and have their life cycle disrupted by being exposed to cell phone radiation. So what do you think could be the way of testing that? It wouldn't be too hard, but what do you think would be the way? So you say one has a cell phone in that case. Okay, yes. But what are they doing with it? And what's up with these bees? Let me know. I'm not trying to make this a tough question. I'm just thinking, quickly you can say to me how a person might go about conducting an experiment on this, explanation. It's not magic. It's not like just sit there and think about bees. I mean, how would you do this? How would you do it? Jillian, you're on the right track. I mean, you say someone's got a cell phone. Can you say more? We just have a cell phone and we've now done the experiment. You have to be a little more precise. Tell me exactly what to be done with it and in relationship to the so-called bees. Just want you to think through the scenario. How would you test that? Okay, so two cases, one without, one with. That's right. So you have a control group, and then you have another group that you expose this dependent variable to. The dependent variable here is the cell phone radiation. So what I guess you would do is get two different bee colonies, have one of them in a controlled environment and another in a controlled environment, but you take the one group and you pump it full of like a bunch of cell phone emissions, radiation, whatever. And the other one, you make sure that it's isolated from any such exposure. Okay, now you have the two groups. One has been exposed to the radiation, the other has been isolated from it. And if this theory of bees dying off from cell phones is true, then what should be the result of the experiment then? What should be the predicted result by the hypothesis? If the hypothesis is correct, then it predicts that in doing such an experiment, what would we find? If the hypothesis is correct, which of course we don't know until we test it, but if it were, in this example, what would be the results of the experiment that you've described there, Jillian? So you would measure the quantity of groups for a set time. The mobile bees should die more often. Yeah, so if this is a correct hypothesis, the prediction of the experimental conclusion is that more of the bees exposed to the radiation should die off, whereas the others don't. Now, that brings us to the fifth and final step of the process. So the last step is simply to evaluate the hypothesis based on the test results. Okay, so now you did your test. Test is done. Now what you do is you compare the results of the test to the prediction of the hypothesis. And that's going to give you one of two answers. Either this test confirmed the hypothesis, or it did not confirm the hypothesis. Either the results of doing the test were what the hypothesis predicted, or it wasn't. So like in our bee cell phone example, if the hypothesis that the bees are dying because of the cell phones is true, then based on the test, we should see them declining in numbers. If nothing happens, if you pump it full of cell phone radiation and the bees don't even die off or seem to have no effect, then that would tend to disconfirm your hypothesis. Okay, so let me write out how the step goes. So the test, let me say it conditionally. Okay, sorry, let me begin again. So if the test confirms the hypothesis, then in that case, publish the results. For others to replicate. If the test disconfirms the hypothesis, then go back to step, and now I want you to tell me what you think that is going to say. So suppose you do the experiment, but it did not confirm the hypothesis. It disconfirmed it. It seemed to not give you the result that the hypothesis predicted. That's disconfirmation. That would be like we pumped the control group full of, we pumped the dependent variable group full of cell phone tower radiation, and it did nothing at all. So the thesis that it was based on the radiation can't be true, or it seems that it's been disproven or disconfirmed. Well, if that didn't work out, then we will have to go back in the steps to what earlier step of the scientific method? Step number what? We tested the hypothesis, but it did not show us that this was correct. And you're right, Judy. We would then go back to step 2, yes. Because step 2 says develop a hypothesis. You don't go back to step 1 because step 1 is identify a problem. Well, the problem is still there, waiting for the correct explanation. But one attempted explanation failed. So if that did fail because the experiment disproved it, then you go back to step 2 and you try a different hypothesis. And you keep going through these steps until finally you get a result that confirms the hypothesis that you're working with. And then that's a successful outcome. Okay, so in science, a lot of times hypotheses are tested and they don't work. So it's not like it's just as easy as come up with some explanation and then do whatever you want from there. No, the explanation that you have is going to be put to the test. And if it's verified by means of the test, great, publish it, and then other members of the scientific community will try to replicate your results by duplicating them in their own laboratory or in their own experimental research. And then more and more scientists keep replicating and repeating the results. The hypothesis gets higher and higher degrees of confirmation. Of course, on the other hand, if it does not get confirmed by the experiment, then you need to try a different hypothesis until finally you get one that is confirmed. One more quick word, since we're talking about the scientific method, which has a lot to do with hypothesis and testing. I want you to know the difference between a hypothesis and a theory, because the words are sometimes used interchangeably. But a theory is just sort of a hypothesis that is graduated to being really, really well proven. So theories are just extremely well-established hypotheses that have been confirmed and reconfirmed many, many times over a long span of time. So theory, a very well confirmed or established hypothesis. Okay, so like every theory starts off as a hypothesis, just someone's educated guess to explain something. But it attains the status of theory by proving itself in the realm of experimental confirmation over and over by a variety of different people. Science never claims absolute 100% truth. It just says this is the most well-confirmed hypothesis available now. And that's just the procedure of science. You know, some hypotheses are well tested and well proven. We consider them theories, which for the most part we think of as true. But we always hold open the logical possibility that even a very well-established hypothesis could be overturned based on new information that we learn later. So science is the pursuit of truth by means of, you know, having well-tested theories. But even as well-tested as a theory is, we always at least leave open in principle the possibility that it could be revised. Okay. So then the next thing to talk about in chapter 12 is this. I wanted to mention briefly how the steps of the scientific method are somewhat similar or parallel to the steps in the critical thinking process. Now, I'm dumbing it down a little bit, and I'm just kind of reducing the steps in the scientific method to the big three. You know, there are 5 there, but 3 are the most key to think about. So you've got experiment, which comes from hypothesis, and the hypothesis comes after you do observation of a problem, right? So you identify a problem, then you create a hypothesis about it, finally you do a test on it. Now, do you guys remember the 3 steps of the critical thinking process? I know that's a little ways back in your mind and notes, but there are these 3 steps that were talked about, and there's some similarity, resemblance that they bear to the steps of the scientific method. So this is scientific method. Over here to the right, I'm going to write critical thinking process. And someone will tell me right now, what are those 3 steps in the process? It's blank, blank, blank. It's something, something, something. What are these 3 blanks that I'm not mentioning so that you'll tell me? Critical thinking starts with this, then it goes to that, and then it leads us to the final and 3rd step. What were those? You got to go back to like it's in chapter 1 type of information, but you learned it, so I'm hoping you'll remember it. Tell me though. 3 steps, critical thinking process. You seem to know it on a midterm. Somebody knew it. Okay. Experience, interpretation, and analysis. That's right. So they kind of are mirrors of these 3 steps here. So the observation stage, where you kind of just identify a problem in the world, that's kind of like the experience stage of critical thinking. After you see something happens, you experience something, just what it is. In critical thinking, you don't just leave it at that. You go forward and you try to interpret why. Why did this event happen? Okay? And then, in critical thinking, once you have your interpretation, you don't even leave it at that. You allow yourself to revisit the interpretation later and to reconsider it if there's a better alternative, and that's analysis. Now, it's not a perfect parallel, but there are definite parallels and similarities between the 2. In science, we observe some unexplained phenomena. We want to know why it happened. But until we get the hypothesis and the experiment, we do not yet know what happened. We do not yet know why it occurred or explain how. We just know that the event did happen. Same in critical thinking. You know, something happens as an experience or an event, but we're not yet trying to explain how or why. Well, when we take the step to the next level, now we are trying to explain why this phenomenon happens. That's what the hypothesis is. Interpretation is much similar, because in interpretation, we try and give our own explanation of why or how some event did happen. And then last, with the scientific method, we put the hypothesis to the test by creating an experiment which can either prove or disprove it. In everyday critical thinking, we analyze our own interpretations, and we put our interpretations to the test. We ask ourselves, do we have the correct interpretation, the correct explanation, or is there a better one that's more accurate to the facts? So the same way that you reflect on your already established explanation is kind of like how you do testing on your available hypothesis for some phenomenon. Okay. See, Biden won the election. What could be the reason? I mean, just now I'd have to guess. Like maybe discontent with the coronavirus. Maybe being somewhat anxious about the economic conditions created by the pandemic, just as an interpretation. And then suppose I want to reconsider that later. Like, well, was it really the pandemic, or did it have more to do with, I don't know, the social justice protests, or did it have more to do with voter turnout, or was it just that Biden was a highly skilled, politician making his campaign? Many explanations are possible, but you allow yourself to reconsider them in the light of all available information. Okay, and in science, you have a phenomenon, try and speculate as to what caused it, then you allow yourself to test it. Okay, so just similarities between the scientific method and the steps of the critical thinking process. Okay, so there's still a little more to say in chapter 12. Some of the last stuff in the chapter talks about what are qualities of a good scientific theory. Okay, so like theories are very well proven, well established hypotheses, but what you need to know is that not all theories or hypotheses are equal. Some are better than others. Some are more successful at explaining the phenomena than others are. And so as a critical thinker, you also need to be able to tell the difference between a good theory or hypothesis and a bad one. So here are qualities of a good scientific hypothesis or theory. Okay, so one quality is simply relevance to the problem being studied. So, I mean, one thing that could disqualify a scientific theory or hypothesis right away would be if it's not even relevant to the subject matter that you're trying to consider. Okay, so like we have more powerful hurricanes that are occurring in hurricane season over the last like 10 years or even 15 years than was measured in generations past. And so that's something that's been noticed, more powerful hurricanes, more active and more numerous. Well, what could be the explanation? Suppose that somebody says, I think I've got the theory. If you look at a graph over that same time period, you'll see that the divorce rate globally has also gone right up. Around half of people getting married in the United States today will get divorced. So maybe there's a connection. Maybe the reason that we have more hurricanes is because more people are getting divorced. I don't know. That's my theory. But that would be a very bad theory, don't you see? Because the two realms are completely disconnected. One has to do with meteorology and weather patterns. The other has to do with social phenomena like making up and breaking up and how long people stay in a relationship. But these two things can't possibly be affected by each other. So unless somebody had a very, very interesting explanation of how they could possibly be connected, it looks like that's not even relevant. So one quality that a good scientific theory must have is at least baseline relevance, being on the same topic and having the same information, at least within the realm of relevance to the problem being studied. Okay. Now, another quality of a good scientific theory is consistency with other well-established theories. What that just basically means is that a good scientific hypothesis or theory will not contradict others that have been well proven. Okay, so a good theory will fit in with and not contradict other theories that have been well proven. Okay, so consistency with other well-proven theories. Science is supposed to be a body of information that all hangs together. So the results of a good scientific theory are supposed to match with mesh with, fit in with the already established body of knowledge that we have scientifically. Because science is supposed to build on the generations of results that have already come before. So it's not like each new generation has to tear down the scientific established truths and rebuild them from scratch. We think of it as a very long process of, sometimes they say, standing on the shoulders of giants. You know, Einstein, he arrives to the scene, but behind him, before him, you've got Newton, and behind that, you've got other earlier physicists and scientists. So a good scientific theory should build on and not contradict, at least, other scientific information. Okay, so like, I don't know, suppose that somebody has a theory that the planet Earth is a flat disk. That would contradict so much other information that we know about how the orbit of satellites works, about how Kepler showed that there's a gravitational attraction that bounds two massive objects in space such that they fall in a smooth ellipsis around the one that's got more mass. So, I mean, we would have to reject so much sound scientific understanding to make space for the flat Earth theory. That's why it's a bad theory, because it can't be accepted without invalidating so many other things that we know to be true, or at least that we think have been well proven. Suppose that you get gifts under your tree on Christmas morning, and your hypothesis as a child is, well, Santa brought these to me. That's my theory. If Santa did deliver those, well, that would contradict so many other things that we know about physics. For example, it would mean that reindeer actually do have a mechanism of flight, even though they're a terrestrial mammal. It would have to mean that you know, the carrying capacity of Santa's sleigh far surpasses anything that should be capable of being suspended in the air by such a small object, because this would have to be a sleigh packed with gifts for millions and millions and millions of people. So it would really defy well-proven laws of physics for us to claim that that is true. Therefore, it's a bad theory. So a good theory fits into, doesn't disqualify or invalidate other well-proven stuff in science. Now, the only exception to that is if there's like a revolutionary new theory, which shows by overwhelming evidence that something that we really all accepted before has to be false. That can happen, but it's usually the exception rather than the rule. So with very few exceptions, it's a good thing if a scientific theory fits right in with the other stuff that's already been established before, that's been well proven so far. Okay. Creating a little room here as we talk about a few more of these qualities of a good scientific theory. A third one is called simplicity. Okay, so simplicity is another really important quality of a good scientific hypothesis. And sometimes this is also referred to under the label of Occam's razor. So what this is all about, simplicity, is the simpler of two explanations for some phenomena is likelier to be true, okay? So the simpler out of two proposed explanations is the one that is likelier to be true. In general, science assumes that the universe is parsimonious and elegant. So what that means in part is that if there are two ways to explain how something happened, and one of those explanations involves fewer assumptions, then it's the one that's probably more likely to be correct. Like, for example, okay, suppose that, you know, I don't know if all of you drive or if you do or don't, but let's imagine that you drive and, you know, you park your car somewhere, you go into like a building to do whatever the thing is, and then you come back out looking for your car. This happens all the time. I mean, I used to use the example of school because I would be giving this lecture in a classroom. It would be like, you guys would park somewhere in the parking lot. But anyway, we have to make adjustment to the example. Suppose, though, that you've parked your car somewhere and now you're returning to the parking space, right? Okay. When you come back, let's suppose that the car's not there. This is a problem. Where's your car? Now you're the scientist, sort of, as you reason through what the hypothesis could be. What's one hypothesis that could explain this phenomenon, that the car is not there where you left it? One hypothesis could be that the reason, the explanation is why. Just throw something out there if you could think of it. Not too crazy of an example. It's probably happened to some of us. I know it's happened to me. But yeah, if you came back to a place where you were parked and the car is not there, so one theory could be stolen. Sure, that would explain it. It would explain why it's not there, because if it is stolen, then it would have been taken away. Another possibility, Shireen, that it got towed. Yeah, sure. Maybe you didn't notice the zone that you were parked in was restricted and it got towed. So maybe it was stolen, maybe it was towed. So let me just choose one of those hypotheses. Let's suppose your hypothesis is that it got towed away. Okay? Now let me give you another hypothesis, a different one, and we'll compare the two, and you can tell me which one you think is simpler. Another one could be the aliens came down, and the aliens abducted my car. So they bust out of Area 51 or whatever they're doing. They found my car. They took it. Okay. So we have two different hypotheses now, and we're just comparing and contrasting them. On the one hand, car was towed. On the other hand, I don't know, maybe it was taken by the space aliens. Now, maybe which one of these would be a simpler explanation with fewer assumptions needed in order to sustain it to be true? Which one's simpler, basically, towing or alien abduction? Definitely towing, yes, because what extra assumptions do you have to make for the alien hypothesis to be true that you don't have to make when it comes to the towing hypothesis? Like for alien abduction to be the real true explanation, you also have to suppose furthermore what other stuff. All kinds of extra stuff now has to be brought on as assumptions. Like you have to assume aliens exist, yes. You also have to assume not just that they exist, but that they're like intelligent enough to build transportation that could take them from whatever planet they are originally from to the planet Earth. So that's another big assumption. Not just that there's aliens like mold spores or like paramecium somewhere in the universe, but like fully intelligent, like interstellar traveling aliens. On top of that, you would also have to assume that they take an interest in your car of all cars for whatever random reason. So, it's getting to be a pretty far off, weird, complex set of facts that have to be assumed to be true for that hypothesis to be considered accurate. So we have two hypotheses, but one of them is way more complex, one is more simple. Occam's razor simplicity requirement or quality says that the simpler of the two is usually the one that you're likelier to accept as true. The textbook mentions the case again of like creationism versus evolution theory. Some people argue that evolutionary theory is a little bit more simple than creationism because evolution theory does not suppose the existence of a being that's outside of the natural universe that can somehow organize and order the things that happen within it. According to evolution, you just need to assume the existence of life forms and mechanisms in nature that lead them towards the specializations that enhance their survival outcome. And so like random variability in the genetic inheritance of the different animals would lead towards the ones having more adaptations that equip them for survival, surviving in greater numbers. So there's fewer things that need to be assumed. No supernatural assumptions or whatever have to be brought to bear for the theory of evolution. Okay, now why is it sometimes called Occam's razor? Well, this is just named after an important medieval philosopher named William of Occam. And he is given credit for first stating this theory, or not this theory, but this principle, that simplicity is a tie-breaking feature to prefer a hypothesis. If both of them can give an explanation, but one is simpler, we prioritize the simpler one and have a greater trust that it's true. Okay, so next up, one more, actually two more. We also have to make a brief mention of falsifiability. Okay, so falsifiability, it just means it's when a scientific theory is able to be proven false. And it's actually a good thing. this is a good thing. It's good when a theory is able to be proven false, because if there's no way to prove it false, then there's no way that it can be confirmed either, right? So for you to test a hypothesis, you have to know what would count as disconfirmation for the hypothesis. Because if you don't know what would constitute disconfirmation, then you're not in a position to claim that it has been confirmed. So if it's unfalsifiable, then it's unscientific because there's no way to test it. So anyway, a good scientific theory is capable of being proven false. Falsifiability, ability to be falsified, to be proven false. Now, don't misunderstand this. Falsifiability doesn't mean that it has been proven false or that it is false. It just means that you know in principle what would have to be shown in order for it to be demonstrated as false. Okay, so like in the case of this bee colony collapse thing, the hypothesis that it is caused by cell phone radiation is falsifiable because you can simply create an experiment which exposes them to that variable. And that's either going to show that they decline in the numbers you predict or it isn't. So that's a hypothesis that can be falsified. But when a hypothesis can't be falsified, then there's no way to test it at all. An example of this could be like, I don't know, take the horoscopes, all right? When you read the astrological signs being predicted, like for a certain date or time period, there's nothing that you can do to show that this was a false prediction, right? If you say, you know what, it said that like a little friend would visit me, but that I would be visited by an old friend, but nobody talked to me at all. I'm on pandemic quarantine and I didn't see any such thing. So that's falsification. You know, the clever astrologist will say, no, you just haven't been paying attention to your own life carefully enough. Like, did you notice that like little bird that perched on your windowsill the other day was tweeting? That must have been what it actually meant. So you didn't falsify it. But that's not good then, because it seems like no matter what we could marshal as a reason to say this is incorrect, we would simply be given another interpretation of the facts so as to rationalize how it was in fact confirmed. So that's not testable. There's no test that an astrology supporter would ever accept, which could, you know, disqualify their belief in the existence of these astrological signs being predicted. Another case, take Freudian psychoanalysis. So Sigmund Freud, some people call him the famous father of modern psychology, and he gets credit for some of that. But he also wrote a lot of really weird stuff that has been pretty much debunked. And some of that, you know, he was high on all kinds of drugs writing it. So anyway, some of these weird things he said, he talked about like that there's like latent sexual attraction from little babies to the opposite sex parents. So like a little girl has the Electra complex, meaning that she sort of secretly harbors like latent sexual desires for the father figure, and that's why when she's older she'll find a man that's similar to the father. Or on the other hand, the little boy suffers from the Oedipus complex, and so he's latent sexual attraction to the mother, and that means he'll find a woman in adult life that's similar to the mom. Okay, anyway, none of that seems to be true according to more detailed research that's been conducted afterwards. But suppose that you wanted to say, I don't think that's true. That's falsifiable because I don't have any such feelings towards my parents. The Freudian would say to you, well, that's what you're telling me, but that's just because you suppressed the awareness of this deep into your subconscious mind. So nothing you say or do can possibly count as falsification for the theory. Well, then we can't possibly test this theory, and therefore it's not scientific. So a good scientific hypothesis or theory provides you with at least the parameters or the means by which you could, in principle, demonstrate that it is false. Okay. I mean, Einstein even, you know, like his theory of relativity, he said, well, this theory, if it's correct, should predict that the next time we have a solar eclipse, that the refraction of light bent around the massive surface of the moon, which is blocking it, should allow us to perceive stars from behind the occluded object because of the bending waves of light. I mean, that's a pretty complex example, but he said, this is something that you should see if my theory is correct. So the next time there's an eclipse, put your telescopes on that part of the sky and see if this is shown. If it is, that's confirmation. And if it's not, that's falsification. But of course, we did the testing. It was not falsified. But even having the ability to test for falsification gave us the ability to gain confirmation. Okay, so one more quality of a good scientific theory is called predictive power. not to be confused with predictability, which was one of the assumptions of science mentioned earlier in the chapter 12 lecture. Predictive power is pretty straightforward. It's just a good theory would be able to accurately predict the occurrence of future events. Okay, so one thing that gives more credibility towards scientific theories is when those type of theories can be used to make predictions that then turn out to be true. And that gives us a sense that these are accurate theories. For example, do we all seem to know when the next solar eclipse will be? Yes. We know the exact time and date. We even know where on the planet you should be if you wanted to have the ideal conditions to view it. And we know this many times, years and years in advance. You can look up right now, like when will be the next full solar eclipse viewable from, the United States West Coast, and you'll get an exact time. Now that's something that then the day comes and the solar eclipse happens exactly on schedule. So that shows you that these people are not just poking around in the dark, coming up with, kind of wild speculation about when things might happen, but that they understand physical principles with a high degree of precision, and that gives us these accurate predictions. I don't know, meteorology, weather predictions, kind of similar. They're not 100% accurate, but they're not that far off. Usually, when the weather forecast says there's a good chance of rain on Friday, it turns out that it usually does rain. And so when we see the confirmation of the accurate predicted result happening, that gives more evidence that these are correct theories. Okay, so the last thing I want to say, and we are really pretty much out of time, but there's only one more note. So I just want to get it in there so that we can say we finished this chapter 12. The last thing it talks about at the end is what's called pseudoscience. And I just want to define this and give you a few examples. Pseudoscience is something that tries to appear to be scientific, but it's really not. So it's a body of explanations that masquerades as science. Full sentence. A body of explanations. This is the textbook definition. They use this funny phrase, masquerades. So masquerade is just kind of like a metaphor. A real masquerade is like you're wearing a mask to conceal your identity. So what it sort of implies is this is a set of explanations that wants people to think of it as scientific in nature, but it's really not. So it's just putting on the false appearance of being scientific, but it's actually not. And what are some examples of pseudoscientific realms of explanation? Well, you've got astrology, you've got like palm reading, crystal ball gazing, tarot cards, numerology, psychics, psychic predictions. All of these fields are not falsifiable. They're not testable. They don't issue predictions that can be falsified in the same way I was describing earlier. A lot of times they make predictions, if they do, that are stated in such vague and non-specific language that almost anything could be credited as confirmation of the prediction. And they mention that in the book where they talk about Nostradamus. So I'll just close with this. Nostradamus famously is a writer from antiquity who some people thought made accurate predictions of all kinds of world events happening later. Some people thought he predicted 9/11 in these ancient writings, but go back and read the words, and it's really weak to think that this is actually a prediction of 9/11. So the relevant passage is this: fire of the center of the earth shall make an earthquake in a new city. Two great rocks shall long time war against each other, and after that they shall color red the fresh water. Huh? I mean, how is that about 9/11? It's something about like two rocks and some red water and a war, but that could be almost anything involving global conflict, involving, the emission of firepower or the loss of life. And notice this too. It's only after the predicted event happens that people go back in time and they say, oh, look, I think I found a prediction of it. It's not like in 1960, people were like, watch out. Have you read Nostradamus? According to him, in 41 years, we're going to have this big terrorist attack, so let's prepare for it. Only after such a thing happens do people try to read obscure writings and then associate a linkage between the two events. So we should not be falling for pseudoscientific arguments or claims. That's one of the #1 things that a critical thinker would not be deceived or tricked by. So expect higher standards of evidence and proof. Try to follow science. Have respect for science, but also know how to distinguish real science from fake science. Pseudoscience literally does mean false science. And so you see the definition here and some examples of that. Okay, guys, well, sorry to keep you for an extra moment. I didn't mean to, but I wanted to make sure we covered the whole chapter. So in 1 week, we will take a quiz on this material, and on Wednesday, we have a day off, but you're still going to turn in your third homework to me over this next week before Wednesday. And I can let you guys know about your scores on that as we head into the weekend. All right, so then have a good day. Everybody's all good. Let me know. Hit the like button or just say, okay, thank you guys, and have a great one. And take care. Enjoy your day off. And happy Veterans Day. Thanks.